conditions are not always simple. So step by step, we are moving toward a difficult level. Previously, in case of dynamic balancing, we considered only single mass on a rotating object. In this lecture, we will consider multiple masses on a same plane, as you can see. So there are 5 different masses placed on a rotor or rotating object, but they all are on the same plane. So let's discuss it. So there are 5 masses: mass m1, m2, m3, m4 and 5. They are placed on a rotor on a single plane. If you count the number of masses on this rotor, then it will be 4. Definitely the 5th mass will be behind somewhere there. Please note that the forces produced by each of the mass will be different. For example, force produced by unbalanced mass m1 is Fm1. Similarly, unbalanced force produced by mass 2 is Fm2. The unbalanced centrifugal force produced by mass 3 is Fm3, Fm4 and Fm5. All these masses are placed at some distance from the axis of rotation. Here the axis of rotation is this point. So mass m1 is placed at r1 distance from the axis of rotation. Mass m2 is placed at r2 angle of rotation, axis of rotation. Mass m3 is placed at a distance, radial distance from the axis of rotation r3. Mass m4 is placed at a radial distance r4. Mass m5 is placed at a radial distance r5 from the axis of rotation. Also, please note that there is a angle between mass m1 and m2. If we take this mass m1 as a reference, so or horizontal plane, or horizontal axis, then the first angle will be angle θ1, which is between mass m1 and m2, or we can say this angle is between horizontal axis and mass m2. The second angle θ2 is angle between the horizontal and mass m2. The third angle, angle θ3, is the angle from the horizontal till here. The fourth angle, angle θ4, is from horizontal till, if we complete the cycle here, till that. So there are a couple of variants here. The things are not much simple because more masses on a single plane. If there are more masses, there will be more forces. Also, their radial distance will be different, and to keep the thing in proportion, we have to measure the angle between mass m2 and horizontal. Please note that the horizontal axis and the axis of this mass m1, they are overlying each other, means theta for m1 will be 0. So θ1 is the angle for mass 2, θ2 is angle for mass 3, θ3 is angle for m4, θ5 is the angle for m5. There are 2 ways to balance the unbalanced system in case of multiple masses on a single plane. In the first approach, what we can do, for example, we have to deal individual unbalanced forces. For example, Fm1 is the centrifugal force produced by this unbalanced force m1. We can use a balanced mass at certain angle at some radial distance in such a way that it will counter the effect of centrifugal force of Fm1. Similarly, we can use a separate balancing mass at certain angle theta in such a way that it will counter the force Fm2. Similarly, we can use a balancing mass at certain angle at some radial distance, such a way that it will counter the centrifugal force produced by this unbalanced mass Fm3. Similar thing has to be happen for Fm4 and Fm5. Or the other approach is that we can counter the effect of all these masses as a resultant unbalanced mass. So this unbalanced mass is equivalent to the force produced by this imbalanced mass will be equivalent or will counter the effect of all the forces produced by the unbalanced mass M1, M2, M3, M4 and 5. I will repeat it again. So the other approach that I'm talking about is that we can, to simplify the system, we can counter all these unbalanced forces, mass M1, force Fm1, mass M2, Fm2, mass M3, force Fm3, Fm4, Fm5. We can counter all these masses as a single mass. Means all other masses are not present and there is only resultant mass or resultant unbalanced mass is present. It has some magnitude, some radial distance, and it's placed at some angle theta with respect to horizontal. So how to find this resultant unbalanced mass? It's very simple way. What we will do, we will start by scaling. We have to say that we have to take some scale. For example, 10 newtons are equal to 1 centimeter. So by taking this scale, we will draw the force Fm1 as an arrow, start from here, ends there, and this magnitude is representing the magnitude of force Fm1. So as this Fm1 is horizontal, no angle theta, so it's horizontal. The second force is Fm2, so the arrow, tail of the second arrow and the head of first arrow, the magnitude of this Fm2 is represented by this arrow, and definitely it's set at some angle theta1. Similarly, the magnitude of arrow represents the magnitude of distance of this arrow represents the magnitude of Fm3 at certain angle theta2 with respect to horizontal. Then the magnitude of force Fm4 is represented by this arrow at certain angle theta3 with respect to horizontal. Similarly, the Fm5 magnitude is represented by this arrow at an angle theta4. At the end, to complete this polygon or to close this polygon, we will draw an arrow. It's drawn in such a way that the tail of resultant arrow will meet the tail of first arrow, and the head of resultant will meet the head of last arrow. So this resultant force is represented by the magnitude of this arrow, and definitely it will be at certain angle theta with respect to horizontal. So here it is, resultant mass at some radial distance at certain angle theta. So all these masses are now gone and they are equivalent to a single mass at some radial distance, and the force produced by this mass is equivalent to the sum of all the forces of the other masses. So now to balance the system, it's very much simple. We just need a single balancing mass at some radial distance, at some angle theta to counter the effect of this resultant mass, or to counter the effect of this resultant mass due to unbalanced masses, or we can counter the this unbalanced mass will produce differently some centrifugal force. So centrifugal force by this balanced mass will counter the centrifugal force by this resultant unbalanced force. So unbalanced force is equivalent to the balanced force, then this means there will be no vibration and the system is balanced. Definitely the masses, like for example the unbalanced mass or resultant unbalanced mass and the balanced mass, they will be somewhat different. Also, if they are different, then their radial distance from the axis of rotation, it will also be different. So this is the whole story about the balancing of multiple masses on a single plane.